Mr. Tarot. In this video, we're going to be talking about simplifying numerical square roots. We're going to do some vocabulary, some properties, talk about how the square root and even power of 2 are going to act as an absolute value function, and then we're going to walk through 8 numerical examples. You're going to find timestamps in the description to jump ahead to any of those examples you like. You'll also find a link to my over 700 math videos that I have produced so far for YouTube. Okay, so simplifying square roots. Well, if a number squared, so if b squared is equal to a, then b is considered a square root of a. Now this is like a variable a, and this is actually the word a. So we have this idea here in numbers to kind of make sense of what that means, that if we take negative 3 and we square it, that's going to be negative 3 times negative 3, which is going to be equal to 9. And we also have the fact that positive 3 squared is also equal to 9. So the fact that we can take the negative 3 or positive 3 and square both of those numbers and get the same answer of 9 means that, well, both positive and negative 3 are considered to be square roots of 9. So that would lead you to think that in your textbook, when you see the square root or radical symbol of 9, that the answer is going to be plus or minus 3, which you kind of can't argue is incorrect, but when you see this radical symbol, this square root symbol, that is going to be used in our book to denote what is called a positive root, or otherwise known as a principal square root. So when you see something in your book, like, well, the square root of 9, we are going to be wanting you to only put the answer down of positive 3, not really plus or minus. Now there will be a time as you go through your studies of mathematics that when you square root a number, we're going to be looking for both the positive and negative answer, but that is going to be more when you're solving algebraic expressions. You'll see that here as we get to the second half of the page. But when you see in your textbook the radical or square root symbol, and there's just a number inside of it, you're not solving an equation, that is going to be equal to, we're going to be looking for just the positive answer. Okay, so, and with the idea that we're looking for that principal root or that positive root, you can kind of think about it in terms of geometry as well. If I give you a square where each of those sides have a length of 3, and I ask you for the area, well then the area of that square is going to be 3 times 3, which is equal to 9. Or, and such, you have a side of 4, another side of 4. Well, if you go to find the area of that square, that's going to be 4 times 4, or 4 squared, which is going to be equal to 16 square units. So you can think of that the result of squaring a number is the area of a square, and the square root of that area is going to be the sides of that square that, you know, created that particular area that you're looking at. Now something interesting happens with squaring and square rooting numbers. If we start with a negative 3 squared, I think actually, let me go ahead and write that out. If I say that I want to calculate negative 3 squared, of course, that power of 2 means that you're going to take the base, write it twice, multiply those together, and of course we get that negative 3 squared is negative 3 times negative 3, which is equal to a positive 9. Now, if you then go and do an inverse function, and you take the square root of 9, you get right back down to 3. Well, math operations like this power of 2 and this square root, which this radical has what's called an index of 2, that square root and that squarine of those numbers, well, in this case, they almost get us back to where we start from. So a squarine and a square root are inverse math operation, but something funny is happening here with the even power and the even root. We started with a negative 3, we squared it, got positive 9, and looked at the square root of that positive 9, knowing that this radical symbol in our textbooks are going to be asking for the primary or positive root. We get down to a positive 3. We started with a negative 3, and we ended with a positive 3. So we see here in this numerical example that a number squared and then square rooted the squaring and square roots are actually acting as an absolute value function. See, the negative went away. We started with -3 squared, got +9, square root of 9, got a +3 instead of the -3 that we started off with. How does that play into the idea that sometimes even roots will give us a positive and a negative answer? Well, if we have here b squared is equal to 9, and I want to solve this equation, even though this is a numerical video, we're going to do a little bit of preview of algebra here. If we square root both sides of that equation, then we have the square root of 9 is equal to 3, but on the left-hand side, with that power of 2 and the index of 2, or the square root of that b squared, that's actually acting, again, as an absolute value symbol. So b squared is equal to 9, as you square root both sides, becomes the absolute value of b is equal to 3. And b then can take on two values that would give ultimately an answer of 3. b can be equal to 3, or b can be equal to -3. So that's how here, with this power of 2 and square root acting as an absolute value function, is where we come into, with our study of algebra, how when we square root both sides of an equation, we get both a positive and a negative answer. And that kind of takes us right back to the beginning with our numerical example, where we have a -3 squared being 9 and a +3 squared being 9. Yeah, really both positive and -3 are square roots of 9, but that radical, one more time, in our textbooks is going to be asking for that principal root. The only time that you're going to be giving a negative answer when a textbook gives you that square root symbol is, well, if there's a negative already out front. And the negative square root of 4 is equal to -2. So let's get on to our examples right now. So example 1, and actually through 8, we are going to be evaluating these expressions, because an evaluate means we're going to be coming up with a numerical value or answer, as opposed to simplifying when we come down to a sort of simplified algebraic expression. So example 1, we have this square root of 36. Okay, well, if we know that 6 squared is equal to 36, then by the definition basically that I gave us at just the beginning of this lesson, we know that therefore if 6 squared is equal to 36, well then the square root of 36 is equal to 6. And for example 1, that's it, we're done. Example 2, we have the square root of 32. Well, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and 6 squared is 36. If we know our powers of 2, then we know that there's no, integer that we can square and get an answer of 32. So either this is our answer, or we're going to be able to simplify this numerical expression, which means that can we find, using this property of multiplication for radicals, we're going to say the square root of a times b is equal to the square root of a times the square root of b. So to quote-unquote evaluate this expression or simplify this expression, what that means is, can you rewrite this? We're still going to leave it in exact form with the radical and, some integer whole number actually on the inside, and not just put this into our calculator and use the decimal that comes out. That would be an approximation. We can simplify this if there is a perfect square, which is a factor of 32. So like 4 squared is 16, and 16 divides evenly into 32 2 times. So this becomes the square root of 16 times the square root of 2, and the square root of 16 is equal to 4. So thus we have 4 times the square root of 2, and our second example is done. Now in number 3, we just used a little bit of the multiplication property of square roots. Really, it's true for all radicals. There's also one for division. A root of a divided by b is equal to that same root, in this case the square root of the numerator divided by the square root of the denominator. And we cannot take, we're specifically in this lesson just talking about square roots, which is an even root. You cannot take an even root of a negative number. unless you want to be involving imaginary numbers, which is beyond the scope of this lesson. So for these multiplication properties of square roots, we need to assume that the numbers that are inside these radicals are greater than or equal to 0. And because you cannot divide by 0, for this definition or property here for square roots, we have to assume the numerator is some value which is greater than or equal to 0, and the denominator is greater than 0 because you can't, again, divide by 0. So with these properties in mind, and looking at the, in this case, the negative square root of 25 over 81, that means that we're going to have a negative, and it doesn't matter if you put it in the numerator, the denominator, or right in the middle of the fraction. That is negative square root of 25 divided by the square root of 81. And as long as you know your powers of 2, 5 squared is 25. So the square root of 25 is 5. The square root of 81 is 9, because 9 squared is 81. And we had a negative out in front of our radical in the first place, so that just carries along, and our answer is negative 5/9. Now with number 4 here, we have a property of basically multiplication property with square roots and a division property with square roots. There is no addition property. This is not equal to simply 2 plus 4, which is equal to 6. Most students will not make the mistake with numerical values inside the radical or square root. They will, however, do that with algebraic expressions, which are to follow. So what you want to do here is you cannot apply the even root to these numbers until you simplify the inside of that expression to be one numerical value. So the square root of 4 plus the square root of 16 is the square root of 20. And that is going to be the final answer in exact form, not just putting it into our calculator and rounding off a decimal, unless we can simplify it, unless we can make the number that's inside the square root smaller. And the only way we can do that is if there's a perfect square, which is a factor of 20. 2 squared is 4, 3 squared is 9, and so on and so on. But 4 is a factor of 20, so we have the factor of 4, or the square root of 4, times the square root of 5, which gives us a final answer of 2 square root of 5. Example 5 coming up right now. Alrighty then. Example number 5 looks just like the previous one, except there's not a negative out front. But it'll have a little bit of extra complexity here. What is the square root of 49 over 50? Well, applying that division property of square roots, we have that's equal to the square root of 49 over the square root of 50. The square root of 49, of course, we know is equal to 7. 7 times 7, or 7 squared, is equal to 49. And the square root of 50, well, 7 squared is 49, and 8 squared is 64. We just jumped over that value of 50. It's not sort of just a simple whole number answer. But there is a perfect square, which is a factor of 50. 5 squared is 25, and 50 divided by 25 is equal to 2. So our denominator is the square root of 25 times the square root of 2, and the square root of 25 is equal to 5. Sorry about smacking my lips there. And this leads us on to the 6th example. What do we do with answers or rational expressions, aka fraction, that has square roots in the denominator? You may be working with fractions that look like this somewhere along your arithmetic and your further math classes after this, but as a final answer, we generally do not like to leave square roots in the denominator, so we do something called rationalizing the denominator. And what did we talk about at the beginning of this lesson? That the squaring function and the square root functions undo each other. So if I want to do something that undoes that square root, then what I will do to that expression is the inverse math operation, which is to square it. And if we assume that x is greater than or equal to 0, then the square root of x is equal to just simply x. So we're going to take the square root of 2 and just sort of square it or multiply it by another square root of 2. But if we multiply the denominator by square root of 2, we need to multiply the numerator by square root of 2. Why is that? Because anything divided by itself is equal to 1. So I'm effectively just multiplying this fraction by a funny looking 1, which is not going to change its value. 5 times 1 is still 5. So that's going to give us 7 times the square root of 2 over 5. Now, you can show as much or as little work as you want here. Ultimately, you're probably just going to write the answer down when you get used to this, but the square root of 2 times the square root of 2 is equal to, with that multiplication property of square roots, the square root of 2 times 2, which is 4, and the square root of 4 is equal to 2. Well, now in the denominator, we have 5 times 2, which is equal to 10, and our final answer is 7 square root of 2 divided by 10. Example number, what, 7? Coming up right now. No. Example 7. Now, as you saw with the properties of multiplication and division of square roots, it's a pretty straightforward situation, as long as they're both square roots, or you can multiply or divide them. But adding and subtracting is a little bit more complicated. You cannot add or subtract square roots unless the number on the inside of that square root, of that radical, doesn't matter really, honestly, if it's a power of 2 or 3 or 4, they have to have the same numbers on the inside, well, and the same index too. So can we simplify the square root of 45 and the square root of 20, basically reduce those square roots in such a way that's going to allow us to, in this case, subtract them? Is there a perfect square in 20? And it doesn't have to be the same perfect square as a factor, but can this be reduced as well? Is there a perfect square that's in 45? Well, yes. A perfect square, which is a factor of 20, is 4. A perfect square, which is a factor of 45, is 9. So we have the square root of 9 times the square root of 5. And with the square root of 20 giving us the square root of 4 times the square root of 5, the square root of 4 is 2. So we have 2 square root of 5. The square root of 9 is 3. So we have now minus the square root of 9 giving us 3 times the square root of 5. And we have now 2 times the square root of 5 minus 3 times the square root of 5. And we basically have two terms here that have common factors of square root of 5. So now what we're going to do is we're going to factor out that square root of 5, basically undistribute it, giving us this first term divided by square root of 5 is going to be 2. This second term divided by the square root of 5 is just going to give us 3. So we have 2 minus 3 in a set of parentheses acting as a coefficient on that common factor that we've taken out of square root of 5. And 2 minus 3 is negative 1 square root of 5. And that is the end of example number 7. Now in example number 8, we have another situation here where we have square roots in the denominator. But now we have two terms. We have a square root of 2. Well, our entire example, is 3 divided by the square root of 2 plus the square root of 5, and our denominator has those two terms which are separated by this plus sign, one term which is square root of 2 and a second term which is square root of 5. How you rationalize this denominator is with the idea that a plus b times a minus b, if we take these two what's called conjugates, two binomials, one with a plus sign in the middle and one with a minus sign in the middle, if we distribute these together, we have a times a, which is a squared, a times negative b, which is negative ab. We have positive b times positive a, which is a plus ab term. And then we have positive b times negative b, which is negative b squared. Well, these inside terms of minus ab and plus ab, hopefully a little bit of this algebraic review of the rule that we're about to use is okay, because this is a video about simplifying numerical expressions, numerical square roots, but we end up here with a squared minus b squared. A plus b times a minus b are the only two sort of style of binomials you can put together. They're called a conjugate pair. These are the only way that you can multiply two binomials and not have a middle term or have it cancel out. So yeah, we're going to multiply this numerator and denominator by the square root of 2 minus the square root of 5, which is, again, numerator and denominator. This is called a conjugate to the square root of 2 plus the square root of 5. So this might be a challenge problem. I'm not sure what level of algebra you're taking right now, but we're going to have 3 times this binomial, so 3 parentheses square root of 2 minus square root of 5, and I'm just going to leave that like that. In the denominator, we have the square root of 2 times the square root of 2, which is the square root of 4. We have the square root of 2 times negative square root of 5. Well, that's going to give us negative, using that multiplication property of square roots, of negative square root of 10, because 2 times 5 is 10. Now moving on to our second term in the first binomial, we have the square root of 5 times the square root of 2, which is, and they're both positive, so plus, again, square root of 10, and then plus square root of 5 times negative, or positive, times negative square root of 5 is a positive times negative is negative, and the square root of 5 times square root of 5 is the square root of 25. Well, of course, the negative square root of 10 plus square root of 10, they have this like sort of an invisible coefficient here that we have. Negative 1 plus 1 is 0, and that's just going to allow those two terms to cancel. Our numerator is 3 square root. Ooh, no, it's not. 3 parentheses, 3 times the square root of 2 minus square root of 5. These are not the same number, nor they can be reduced, so this is just as simple as it gets. The denominator is square root of 4, which is 2, minus the square root of 25, which is 5. And so our final answer is equal to 3 times the square root of 2 minus square root of 5 over 2 minus 5 is negative 3, and 3 divided by negative 3 is going to cancel out to give us basically a negative 1. So our final answer is negative square root of 2 minus square root of 5. And I'm Mr. True. Bam! Go do your homework.